Hey friends, welcome. Today we will be discussing the second part of Debye Huckel theory. This is also known as Debye Huckel limiting law. This will be the continuation of the last part, wherein we have derived the expression for the electrical potential psi, and that was Zi epsilon by Tr minus Zi epsilon kappa by D. So this was the last expression that we have obtained when we were discussing Debye Huckel theory, and we have also seen that the first part is due to the self potential of the ion, and the second part is due to the ionic atmosphere that is formed in the case of strong electrolytes, and this makes the strong electrolytes different from the weak electrolytes. Basically, again, we will be starting with the amount of work done, and we will be defining the amount of work done for the process of charging of the ion, that is when we are bringing any particular ion from the infinitely dilute solution to a given dilution. So basically what we are doing over here is we are generating the ionic atmosphere. We have all discussed in our previous lecture that when the ions are for very dilute solution, the distance between the ions will be very large, and that could be considered as infinite distance. Now in a given dilution surrounding several positive ions, there will be several negative ions, and surrounding several negative ions there will be several positive ions, and this will form the ionic atmosphere. So when we are charging, so that is we are bringing the charge from the infinitely dilute solution to a given dilution. So in a given dilution, what will happen is that there is a formation of ionic atmosphere, and this ionic atmosphere makes the strong electrolytes different. Okay, so this process of charging, we can consider it as the amount of work done when we are charging an infinitely dilute solution. Suppose if we say that W1 is the amount of work done when we are charging an infinitely dilute solution, and similarly the amount of work done when we are charging a given solution of a finite dilution W2, then the work done delta W will be the difference between the work done when we are charging a finitely dilute solution and work done when we are charging very dilute or infinitely dilute solution. So this will give us the amount of work done when we are charging any particular solution. Okay, now over here, in order to obtain the work done, if we are considering that psi is the electrical potential, and over here when we are charging any particular solution, then we are bringing up a very small amount of charge d epsilon. Okay, because we all know that epsilon is the charge. So over here we all know that when we are charging any particular thing, then the charges will not accumulate directly, or the charging will take place slowly, like we are charging the mobiles. So our phone is charging very slowly, the reactions are getting, or the potential is being built up gradually. So similarly over here also, when we are charging the infinitely dilute solution as well as charging the finitely dilute solution, the charges are accumulating slowly. And suppose if we say that d epsilon is the amount of the charge that is being added gradually, then the amount of work done will be the amount of work done, and the initially when at infinitely dilute solution the amount of charge will be 0, and at finite dilute solution we know that the total charge on any particular ion is Zi epsilon. So when at infinitely dilute solution, the limit of integration will be from 0 to Zi epsilon, because these are the small charges, and we know that integration is a function wherein these small charges are added up. Okay, so the amount of work done W will be given as integration 0 to Zi epsilon psi d epsilon. Okay, so d epsilon is the small amount of charge that is being generated. Now we have the value of psi that is over here, and we will not be taking zi over here. We will be directly taking epsilon by dr. Similarly, epsilon kappa by dr over here. So we will be substituting the value of psi for both the cases. First, we will be looking at when we are charging an infinitely dilute solution, and then when we will be charging a finitely solution. Okay, so for the first case, when we are charging an infinitely dilute solution, then in case of an infinitely dilute solution, we know that the potential at any particular point will be due to the self potential, because in case of an infinitely dilute solution, the distance between the ions will be very large, and as the distance between ions is very large, the potential at that particular point will be due to the self potential, and hence the value of psi will be epsilon by dr only. Okay, so our work done, W will be equal to integration 0 to zi epsilon by dr into d epsilon. So over here dr is constant, and integration of x dx will be x square by 2. So we will have 1 upon dr, we will keep outside, and we will have epsilon square 0 to zi epsilon, and that will be upper limit minus lower limit, and we will have, so upper limit lower limit will be 0, so we will have zi square epsilon square upon dr. This will be, okay, x square, it is integration of x dx is x square by 2, so this will be zi square epsilon square by 2 dr. Okay, similarly, so this is the amount of work done when we are charging our solution in an infinitely dilute solution. Similarly, for a finite solution or for a given solution, amount of work done, W will be equal to integration 0 to zi epsilon dr. I will separate the integrations for both the terms, that is d epsilon minus integration 0 to zi epsilon. We will have epsilon kappa by d. Okay, and again integration x dx will be x square by 2, so we will have, I will keep 1 upon dr outside, epsilon square by 2 0 to zi epsilon minus, again over here kappa by 2, and we can keep this 2 outside, so we will have epsilon, this is d epsilon 0 to zi epsilon, and hence we will have zi square epsilon square by 2 dr minus zi square epsilon square kappa by 2 dr. Okay, so this is our W1 and this will be our W2. So this is the amount of work done when we are charging a given solution, and as we have seen, the net amount of work done will be W2 minus W1. So W2 minus W1, this is W2 minus W1. So both these terms, let me do it. Net amount of work done is W2 minus W1, and that is zi square epsilon square upon 2 dr minus zi square epsilon square kappa by 2d minus, we will have zi square epsilon square upon 2 dr. So both these terms will be cancelled out, and we are left with minus zi square epsilon square kappa by 2d, and that is the amount of work done when we are charging our solution from an infinitely dilute solution to a given dilution. Okay, now this charging, basically it corresponds to the amount of electrical energy that is being generated. Okay, and the amount of electrical energy, so hence this work done, or the amount of work done that could be represented in the form of electrical energy EI. Also, this is the amount of work done when we are charging a single ion. Okay, this is the amount of charge that is generated, or this is the amount of work done when we are charging a single ion. So for say 1 mole of any particular ion, or for any particular molar solution, the for molar solution we know that that is equal to Avogadro's number. 1 mole is equal to Avogadro's number. So I could write Na, or I'll be writing only N for Avogadro's number. So when we multiply this expression with N, so that will give us the amount of the electrical work done for charging say 1 mole of any particular work done for any particular solution. Okay, now further we will be moving on to the definition of chemical potential. Now for chemical potential, we know that chemical potential we will be looking at two different cases, that is for ideal solution. For ideal solution, chemical potential mu I, we could write it as mu I is equal to mu 0 plus RT ln xi, where xi is the mole fraction of the system, and R, we know real gas constant is the temperature, and mu 0 is the standard chemical potential in the standard state, or chemical potential in the standard state. So this is the expression for the chemical potential in case of an ideal solution. Now for non-ideal solution, generally for non-ideal solution, over here xi, it represents the concentration. So in case of non-ideal solution, we use the term activity in place of the concentration, and hence for non-ideal solution the expression will become mu I is equal to mu 0 plus RT ln AI, where AI is the activity of the solution. Now activity, basically this can be defined as the effective concentration of any particular ion in a solution, and activity is related to the concentration terms by activity coefficient. That is, activity AI, it is related to mole fraction by activity AI is equal to gamma I into xi. This could be written in this particular manner, where gamma I is the activity coefficient. Okay, gamma I is the activity coefficient. So our expression will become mu I is equal to mu 0 plus RT ln xi plus RT ln gamma I. Okay, so this is the expression for the ionic, this is the expression for the chemical potential for the non-ideal solution, and this is the expression for chemical potential for an ideal solution. Now when we compare both these expressions, then we will see that in case of non-ideal solution, this much term is greater. Okay, this much term is greater as compared to the ideal solution, and this greater term, it represents the free energy which is accompanied by adding say 1 mole of any particular 1 mole of ionic species in the solution. Okay, so when we are comparing ideal and non-ideal, so this ideal solutions, it is similar to the dilute solutions also. So as we can see clearly that this additional term which is occurring in the non-ideal solution is basically because of the formation of the ionic atmosphere. Okay, and over here this energy, it is also the amount of energy required for the formation of the ionic atmosphere, because we have seen this is the amount of work done when we are bringing any particular charge from an infinite dilute solution to a given solution, and when we are bringing the charge from an infinite dilute solution to a given solution, then we are preparing or we are forming an ionic atmosphere. Okay, so this is the amount of work done when we are forming an ionic atmosphere, and similarly this term is occurring also because of the ionic atmosphere. So hence we could equate both these terms, and both these terms are one and the same. This is also representing the amount of energy for the formation of ionic atmosphere, and this is also representing the amount of energy for the formation of ionic atmosphere. Hence we could write RT ln gamma I is equal to n into we had minus zi square epsilon square kappa by 2d. So Na into minus zi square epsilon square kappa by 2d. This we could rearrange by writing or by taking this RT on right hand side. So this will be dRT, and RT from here we will be removing it. Further, in our previous lecture we have seen the value of kappa, okay, and the value of kappa, it is 4 pi epsilon square summation Na square upon dkt, and this is kappa square. Okay, so this is the value of kappa that we have seen in our previous lecture. Now what will be now over here, Ni are the number of ions, so we will be using this value of kappa and we will be substituting this kappa in this equation over here. Okay, so this I could write it as to the power 1 by 2, okay, under root I will be writing as to the power 1 by 2, and we will be substituting the value of kappa. Also Ni are the number of ions per cubic centimeter, and this could be written in the form of concentration, and this we will be writing as N, that is Na into Ci upon 1000. So this is the definition of the concentration, where Ci is the number of grams per liter. So this is Ni are the number of ions per cubic centimeter, and this could be written in the terms of molarity. And similarly K over here is similarly K over here is the Boltzmann constant, and K we could write it as R by N. Okay, K could be written as R by N, so that we will be replacing it by R by N. So when we use both these terms in this expression and we will be substituting over here, so we will have log of gamma I is equal to minus Na zi square epsilon square upon 2d RT. This will remain as such. We will have 4 pi epsilon square. This will be summation Ni, we are writing it as Na Ci zi square upon, we will have dr, Na in the denominator will go in the numerator, and we will have into Na drt, and then this 1000 will come into the denominator, and this will be 1000 to the power 1 by 2. Okay, now we can take Na outside, so this will Na and this will become Na square. So we will take Na outside, so this is Na square. Similarly we will take this 2 inside over here, so this will become 4, and I could write 2 into 2. Similarly this 4 I could write 2 into 2, so this 2 will be cancelled out. Why I am doing it, I will be just telling it again. This epsilon square I will be taking it out, so this epsilon square will come out, this epsilon we have, and it will become epsilon cube zi square. I will write it as it is upon, over here also we have drt, over here also we have drt, so this will be drt raised to 1, and plus we will have 1 by 2, so that will be drt raised to 3 by 2. In order to avoid the confusion, let me write it in this particular manner, that is we will have dt raised to 3 by 2 and r raised to 3 by 2. Okay, then we are left with this 2 pi by 1000. So this I will be writing it as 2 pi by 1000 raised to 1 by 2, and we are left with now half summation ci zi square, and half summation ci zi square, it is nothing but it is the ionic strength mu. Okay, so half summation ci zi square, it is nothing but it is the ionic strength of the solution. So half summation ci zi square, that I will be writing it as the ionic strength, and that will be under root of mu will be written as the ionic strength of the solution. Okay, now over here the constant terms I will be equating it to a dash. The constant terms, constant we have Na epsilon cube 2 pi by 1000 to the 1000 to the power 1 by 2. So we will have also in the denominator we have r to the power 3 by 2. So this term, this term, this term and this term, so that we are taking it as a dash. So we will have minus a dash, we are left with zi square under root mu by dt raised to 3 by 2. So this is our expression after substituting the terms. Now further, for a specific temperature and specific solvent, d and t are also constant. That is, suppose I am taking water as a solvent and temperature 25 degrees centigrade, then in that case d and t also will be constant. So we are defining one more constant a, which is equal to a dash upon dt raised to 3 by 2. Okay, so hence I will be substituting in place of a dash by dt raised to 3 by 2, I will be substituting a zi square under root mu. Okay, this is minus. Okay, so this is the expression, that is log of gamma I is equal to minus a zi square under root of mu. This expression gives us the value of activity coefficient, that is log of gamma I. So in place of gamma I could write it as either say log of gamma plus, or I could write it as log of gamma minus. Okay, but it is very difficult to find out the individually activity coefficients of the cations and anions respectively. So in order to do that, we will be using one more term, that is we will be using the mean ionic activity coefficient. Okay, and to do that, first let me write the previous expression, that is log of gamma I is equal to minus a zi square under root mu. Okay, so we will be finding, in order to find out activity coefficient, we will be using the mean ionic activity coefficient. And for that, suppose again we are using 1 mole of any particular electrolyte, and that 1 mole of electrolyte it dissociates say total V amount of ion, wherein we have V plus amount of cation and V minus amount of anions. Then the total amount of ions V will be represented as V plus plus V minus, where V plus is the amount of cations and V minus is the amount of anions. Now the activity coefficient that is mean activity coefficient, gamma plus minus is written as mean activity coefficient. So mean activity coefficient to the power total number of ions will be equal to activity coefficient of the ions to the power V plus into activity coefficient of the anion to the power V minus. Okay, so this is the relationship between the activity coefficients of the ions and the mean ionic activity coefficient. Now this we could rearrange the expression, that is I can take logarithm on both hand sides. So we know that log of power will come front, and we will have log of gamma plus minus is equal to V plus log of gamma plus V minus log of gamma minus, and V over here I am taking directly into the denominator, and this I could write in this particular manner. So I could write it in this particular manner. Similarly, this v, we know it is v plus plus v minus, so this could be written as v plus plus v minus also. Okay, further we know the value of log gamma plus and log gamma minus from this expression, that is log of gamma plus, I could write it as minus a z plus square under root mu, and log of gamma minus will be equal to minus a z minus square under root mu. Okay, this we all know it. Also, where again z plus and z minus are the valencies of the cations and anions respectively. Also, we are very much familiar with the electrical neutrality of the solution, that is the solutions are electrically neutral, and hence the total charge, that is the total amount of cations, that is v plus z plus, is always equal to v minus z minus, that is total positive charge is always equal to the total negative charge, and this we could rearrange in this particular form, that is v plus upon v minus is equal to, we will have z minus upon z plus. Okay, so first both these expressions we will be substituting over here, and then in place of, let's do it first. So we will have a log of gamma plus minus is equal to v plus, so this is minus, so I'll put minus front, minus a z plus square under root mu minus v minus a z minus square under root mu, and this will be v plus plus v minus. Okay, now from this relationship, what we could do is we could take v plus, this is v minus, so v plus is equal to v minus z minus by z plus. Okay, and this relationship we will be substituting over here. Okay, this relationship will be substituting over here. So when we substitute that over here, we will have this will become v minus z minus upon z plus, and we can take the common denominator, and then this denominator could go in the numerator. Okay, also the common terms I can take it out, that is I can take a under root u, I can take minus also common out from both the terms, and then over here we have v plus z plus. So in place of v plus z plus, we could substitute v minus z minus, so we will have v minus z minus over here, and we are left with 1 z plus. Okay, so this v plus z plus from here and this v plus z plus from here, so sorry, v minus z minus from here and v minus z minus from the first term, I will be taking common out, so we are left with z plus plus z minus, and this z plus will go in the numerator, so we will have z plus. Also v minus we could take common out from both these terms, so we will have z plus, sorry, this is z minus plus z plus. So this term will be cancelled out, and hence our expression will be log of gamma plus minus is equal to minus a z plus z minus under root mu, denominator, all the terms from the denominator are being cancelled out, so we will have minus a z plus z minus under root mu, and this is our final expression, which is the celebrated Debye Huckel limiting law, which gives us the value of the mean ionic activity coefficient. And over here A is constant, and for water as a solvent and at 25 degrees centigrade the value of A is 0.509. Z plus Z minus are the valencies of cations and anions respectively, and mu is the ionic strength of the solution. So this is our final expression for the Debye Huckel limiting law, which is applicable to the dilute solutions of the strong electrolytes. And from this expression we could also say that the temperature of the ideal behavior, it is governed by the ionic strength and the ionic strength of the medium and the valencies of the ions of the electrolyte. Okay, so this is our final expression. I hope the derivation was clear. Thank you very much.